Okay, class, this is notes for 9394. This is going to go very quickly. We got polarity and bond overlap. So in chapter 8, we discussed the bond dipoles. Now, bond dipoles is simply a look at the electronegativity, 3.5 on this side, 3.5 on this side. And it doesn't really matter what carbon is on this side because bond polarity is the electrons are being pulled to the outside of both of them. But here's the deal. The problem is that when you have something that has equal electronegativity on both sides, it really doesn't matter with the geometry. Now the geometry steps into whether or not this is a polar or a nonpolar molecule. This is carbon dioxide. Carbon dioxide would be considered a polar molecule except for the fact that the oxygen on either side is pulling equally. So you really have a nonpolar situation. Okay, now this is a little bit different than what we talked about before. Remember we talked about like the difference between HF at 4.0 and 2.2 or whatever it is, and the deal is that this is a very polar molecule, and it's polar because we have an unevenness of electronegativity. But down here for carbon dioxide, it's very even because you have the same strength pulling on the outsides of this molecule, which because of the geometry, they cancel each other out. So this ends up being non-polar no matter what the difference is between oxygen and carbon. So whenever we have, now that we know the geometries, whenever we have one of the five shapes that's linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral, whenever we have those five shapes are non-polar because they pull equal in all directions. So that there's no one spot that is more polar or has a higher electronegativity or a pull on electrons than another spot. So this is non-polar, not because of the difference of electronegativity. The CO2 here that I'm looking at, that I just circled, is non-polar not because of the CO2, not because of the difference in negativity between carbon and oxygen, but because geometrically the oxygens on the outsides are pulling at the same strength, which equals out, which cancels out the pull from one side to the other. So as long as you have an equal pull on all sides here, which you do, then it's non-polar. Whereas something like HF is clearly polar because there's clearly a spot here where the electrons are being pulled the strongest, as opposed to the other side with the H. Okay, so let's keep going and see if we can figure this out a little bit better. So notice that for water here, I have oxygen at 3.5. Okay, now notice that this is unequal. I have 2.2 for hydrogen and 2.2 for hydrogen here. And what happens is the oxygen, because it's stronger in electronegativity, pulls the electrons closer to itself like this, and we get what's called like a positive area down here. The hydrogens are just one proton, which means it produces a positive area, and because oxygen is pulling all the electrons up here, we get a partial negative area at the top there. So this right here is a sign that we use for partial. In other words, if I have a partial negative area up here on this end of the water molecule, it means that it tends to be negative, but not a negative, not like a full minus charge. It just has like a negative area to it. So this has a dipole moment. The dipole moment overall is shown from this, like the combination of the two hydrogens, including the geometry. And the geometry here is a bent molecule, which is not symmetrical. And that's really the key. If we had a symmetrical situation, then we would have a nonpolar molecule. So take a look here. Here we have a non-symmetrical situation, so this is a polar molecule. However, with carbon and chlorine on the outsides here, because this is tetrahedral in one of our five shapes, it doesn't matter what's on the inside and what's on the outside. As long as everything on the outside is the same, we have a symmetrical situation, which automatically means it's nonpolar. Okay, notice that over here for NH3, we have a polar molecule. It's polar because this is definitely not symmetrical. Even though we do have H's here, here, and here, because the lone pair that's up there, it is not symmetrical, which means that there's a difference between the two of them. Here we have another situation where it's polar, even though this is a tetrahedral, because we have chlorine here and hydrogen here. Obviously chlorine with 3.0 is more electronegative than the 2.2 for the hydrogen, which means that it's pulling electrons closer to the chlorine. So that would be a polar molecule. Notice here, though, we have a nonpolar situation. The fluorine is very electronegative. It's 4.0. It's the strongest one for pulling electrons. But the boron here in the middle, it doesn't even matter what, I think boron's 1.8, but that doesn't even make a difference simply because the fluorine is pulling out with equal strength, which makes this whole system here nonpolar. There are no lone pairs on boron, and it's trigonal planar, which means that with symmetry, fluorine is pulling out at equal strength at each one of the fluorines. So that makes it nonpolar. So what about overlapping and bonding? So here you have a situation where you have the hydrogens overlapping. Remember that hydrogen is 1s1 and this one is 1s1. And when they combine, they overlap with a spherical shape. That's why you see hydrogen looking like this. But the difference is that hydrogen has the spherical shape, but because chlorine is 2p, where are we at here? Chlorine is 3p, I believe. Yep. So that would be 3p5, and because of the p means that we have the dumbbell shape like this. So that means that part of the dumbbell shape is overlapping with the spherical shape from the hydrogen, and that's where you get the overlap, and that's where you get the bond to happen. Same thing here with Cl2. You get a P shape here and a P shape there. Maybe I could use a different color. P shape there and P shape there, and then the overlapping area there is where the bond happens between the three P's. Okay? So notice what happens when we push two hydrogen atoms very close together. The amount of energy it takes to keep them there is very high. We're over on this side. So when we push them together, the nuclei are now, the plus and the plus are pushing off on each other with a lot of force. But as we move along, notice the force of them pushing off drops down to a trough area here where we have electron on one attracted to the nucleus of the other and an electron of the other attracted to the nucleus. So we have our attractions now that have taken hold. But as we get further apart here, then we get electron-electron repulsion here. And then these are too far apart to even make a difference, which is why it kind of goes towards zero. Zero is here. Okay, so our zero line is this right here. And the further away we get, the further closer to zero we get. But notice how much energy is up here when you push the two atoms very close together, because the nuclei obviously push off on each other. What this is trying to show you is that there is like a spot here that happens to be about 0.74 angstroms where the nuclei are that far from each other. And that seems to be the sweet spot where the hydrogen atom, like this hydrogen 1 and hydrogen 2, the 1 atom is attracted to the electrons of 2, and the 2 atom is attracted to the electrons of 1. And when that happens, this is where we form the bond between the two of them. Okay, so notice energy goes up when we get them too close, and it goes up when we get them too far away. So that's why forming a bond actually gives off this amount of energy. Okay, that's why it's a negative, because it gives off that much energy when you form a bond. Okay, that's it. Nice, quick, and easy. We'll see you for 9, what would that be, 9.5 and 9.6.